Hey, I'm Charlie Thompson, and this is the Lab 7 Atmospheric Stability How-To video. So in this video, I thought I would take the three types of questions that you're being asked on the lab assignment itself, and then go through those step by step. So the first kind of question is you're just going to take a parcel and lift it up and find its dew point temperature, the lifting condensation level, the final specific humidity, and then also the grams per kilogram of water vapor that condensed out as that parcel rose and cooled. So I made up this one based on actual conditions on Kauai, where orographic lifting produces some of the highest rainfall rates in the world. We're going to take a parcel of air from sea level and lift it up to the summit of Mount Waialeale at 1570 meters above sea level. So I will set up each problem. The givens are, we know how far it's going to get lifted up. We know the temperature of the parcel and its relative humidity. So the first question we need to find out is, what's the parcel's initial specific humidity? And we can find that out because we know its temperature, 28 Celsius, and its relative humidity, 95%. So we know that it's got 95% of the maximum. So we look it up on the table at 28 Celsius. The maximum specific humidity is 24.3 grams. We multiply that by 95%, 0.95, and we get 23.1 grams per kilogram for the parcel's initial specific humidity. Once we know the specific humidity, 23.1 grams, we can then look that up on the chart to find the dew point temperature. So if you have 23.1 grams of water vapor, the dew point temperature is going to be 27 degrees Celsius. So now we know the dew point temperature, and we can find the lifting condensation level, because its temperature on the ground is 28 degrees. Its temperature, the dew point temperature is 27. So 28 degrees minus 27 degrees equals 1 degree of cooling. If you take the number of degrees that it has to cool and you divide that by 10, that'll give you the answer of how much it's going to have to rise before it cools to dew point temperature. In this case, it's 0.1 kilometers, 100 meters. Once the parcel rises just 100 meters, it's going to cool by a degree. It'll hit dew point temperature. We'll get condensation. And then we'll have to cool it at the moist rate because it's cooled to dew point. Condensation's happening, which releases heat. So we know the parcel is 27 degrees at 0.1 kilometers. It's going to go from 0.1 up to 1.57 kilometers. So it's going to get lifted up. Do the math over here, 1.57 kilometers minus its starting altitude of 0.1. So it's going to have to go up 1.47 kilometers. It's cooling at the moist rate of 6 degrees. So it's going to cool by 8.8 degrees. It was 27 at dew point temperature, 27 minus 8.8, 18.2 Celsius. So the parcel's temperature at 1570 meters is going to be 18.2 Celsius. Now that we have the temperature, we can look up and find what the maximum specific humidity is. Given a dew point temperature of 18.2 Celsius, or actually the temperature is 18.2, that's going to round to 18 because we're looking for a dew point. The dew point temperatures on the chart are all integers, they're all whole numbers. So once you find what the actual temperature is, you round that to the nearest degree, look it up on the chart. At 18 Celsius, the maximum specific humidity is 13.1 grams per kilogram. So, as the parcel cooled, you get condensation, and what you're left with is 13.1. What we started with was 23.1. So, the last question, how many grams of water vapor condensed? We had 23.1. We end with 13.1. The difference between those is 10.0 grams per kilogram. So, on the assignment, you'd enter that as 10.0. All right, that was the first one. We're just taking air, we're lifting it up, we're seeing what happens to the temperature, we're seeing what happens to the water vapor. Okay, and the last type of problem. We're going to take a parcel of air, we're going to lift it up to the summit, and then we're going to drop it down to simulate the rain shadow effect. So for this problem, we're going to find the dew point temperature, the lifting condensation level, the final specific humidity at the summit, the grams per kilogram of water vapor lost on the way to the summit, the temperature of the atmosphere at the summit, so we'll use the environmental lapse rate to calculate that. And then finally, we're just going to find out if the parcel is stable or unstable at the summit. After it hits the summit, we've run out of up, so it's going to sink. And then we're going to find the ending temperature after it's sunk, the specific humidity, and the relative humidity. So in this exercise, we'll take a parcel of air from sea level to the summit of Mount Rainier at 4,400 meters, and then we'll drop it down into Yakima, Washington with an elevation of 300 meters. So Mount Rainier is on the windward side of the Cascades. So as storms come in off the Pacific, they run into Mount Rainier, they get lifted up. The ranger station gets about 126 inches of rain a year at Mount Rainier. After it goes over the summit of Mount Rainier, there's nothing higher. And so if conditions are stable and the air sinks, it's going to sink a considerable distance. Yakima, Washington is in the rain shadow, and they get about 8 inches of rain a year. So Mount Rainier, 126 inches, Yakima, about 8 inches. So we're given an air parcel at sea level at 15 Celsius. It's got 40% relative humidity. The environmental lapse rate is 7 degrees of cooling for every kilometer you go up. And we're going to answer the following questions. If we take that parcel of air at 15 Celsius with 40% relative humidity and we lift it up, the first thing we're going to have to find is the dew point temperature. So we know the formula for that. Specific humidity equals the max specific humidity times the relative humidity. We look it up on the chart. At 15 Celsius, the max specific humidity is 10.6 grams. We're going to multiply that by 0.4 because we only have 40% of the maximum, which is going to be 4.2 grams. We look that up on the chart and we get a dew point temperature of 1 degree Celsius. Once we know the dew point temperature, we can figure out the lifting condensation level. So the temperature on the ground is 15, the dew point is 1, 15 degrees minus 10 degrees is 14 degrees of cooling. The air is going to cool 10 degrees for every kilometer, so the lifting condensation level is going to be 1.4 kilometers. If we want to find the temperature of the parcel at 4.4 kilometers, remember it cooled to dew point temperature at the lifting condensation level, so we know that its temperature was 1 degree Celsius at the lifting condensation level of 1.4 kilometers. From 1.4 to 4.4 kilometers is 3 kilometers of lifting. It's going to get lifted by 3 kilometers. Now it's cooling at the moist rate of 6 degrees per kilometer, so it'll be 18 degrees cooler. So the temperature of the parcel will be negative 17.0. Notice, because this is a parcel temperature or an atmospheric temperature, I've rounded it to 1 decimal place. Dew point temperatures, round those to a whole number. Lifting condensation level, round that to a tenth. And the next question, what's the specific humidity of the parcel? Well, we know what the temperature is, so all we have to do is look it up on the chart, and we can find out the maximum specific humidity at negative 17 degrees Celsius is 1.1 grams of water vapor per kilogram of air. If we want to find the temperature of the atmosphere, that's pretty easy. We're going from sea level to 4.4 kilometers. We're cooling by 7 degrees a kilometer. So the atmosphere is going to be 30.8 degrees cooler than it was when we started. 15 minus 30.8, negative 13 Celsius. And that also means that the parcel of air is stable. The temperature of the parcel is negative 17. The atmosphere around it is negative 13. So the parcel is cooler, so it's not going to rise anymore. So as the parcel sinks from 4.4 kilometers to 300 meters, it's going to warm by 10 degrees per kilometer. 4.4 to 0.3, that's going to be 4.1 kilometers of sinking. It's going to heat up 10 degrees per kilometer, so it's going to be warmer by 41 degrees. The difference between 41 degrees and 17 degrees is 24 degrees, so now we know the new temperature for the parcel at 300 meters over in Yakima. Once we know the temperature's parcel, we can figure out what the relative humidity is, because the specific humidity is unchanged. Once the parcel cooled down to negative 17, everything in excess of 1.1 grams of water vapor condensed out. So that's all that's left. As the parcel sinks, it's going to warm up, but it's not going to get more water vapor. It's just going to keep whatever the lowest value of specific humidity is. As the parcel warms, the maximum is going to increase, but it's not going to pick up more water vapor if there isn't water vapor to pick up. So now we know what the parcel's specific humidity still is. We know what its new temperature is. So relative humidity equals specific humidity 1.1 divided by the maximum. The maximum from the chart is 18.9. 1.1 divided by 18.9 works out to 0.058. Multiply that by 100, round to a whole number, and we get the parcel's relative humidity on the ground now in Yakima is 6% relative humidity. Incredibly dry, which explains why Yakima only gets 8 inches of rain a year. So that's it for the Lab 7 Atmospheric Stability How-To video. I hope that makes it easier for you to deal with the problems on the Lab 7 activity. If you have any questions, please let me know. I'll set up a Zoom session. We'll figure it out.